Okay, I just gave back your quiz 2, and we're going to have another quiz this Thursday, give you a chance to bring the scores up a little bit. I think the average maybe isn't quite what you'd like at this point, but that's okay. You can bring it up. And most of you still have over 100% anyway because of those bonus points you earned on the concept inventory. So I don't think anybody's sweating grade stuff at this point. Homework 4 is due on Thursday, and a week after that we'll have our midterm exam, October 5th. So what I'd suggest you start doing for the midterm exam is reviewing those concepts, you know, the list of important terminology from the text. I'd suggest that you start, I don't know, making flashcards or refreshing your memory on those definitions, because that will be a big part of the exam. Probably 35% of the points will be related just to short answer questions. All right, we're going to continue talking about evaporation today. And last time we left off talking about the energy method. And who wants to take a crack at summarizing like the conceptual basis of the energy method? What is it? It's predicting evaporation on the basis of what? All right, the sun coming in and coming out. So the difference between the two, the incoming solar radiation and the outgoing radiation that's emitted, the difference between the two is free energy that's driving evaporation. And so just to summarize the process that we went through previously, we calculated the latent heat of vaporization, which is how much energy in terms of joules per kilogram is required to go from liquid to vapor. And then we go through the process of calculating how much net energy is available to drive that evaporation. And so the net energy takes into consideration the reflection off of the surface of the water, and it also takes into account the emission of long-wave radiation. And then the evaporation is just calculated once we know how much energy is available on the latent heat of vaporization. Now, we didn't actually use either of these terms in the previous example, but you'll note that here I've highlighted 75% humidity and a wind speed of 1.7 meters per second. Just to make the next example a little bit more interesting, I changed it from their previous values to those values. So if you've printed out the notes for the next example we work, please be sure to make the correction in the notes. Are there any questions about the energy view of things when it comes to evaporation? Okay. Now remember that it's not just how much energy is available, but it's also the gradient between saturated conditions and our current moisture conditions in the air. So the next approach that we're going to look at, the aerodynamic method, asks the question, how quickly can water that's evaporated from the liquid phase, how quickly can that vapor be moved away from the water's surface? And if you think about the conditions very close to the water surface, you might rightly guess that it's more humid in the immediate vicinity of the water surface than it is some distance up above the water. And so there is transport going on, and the difference between how humid it is in the air and how humid it could be in the air, that gradient is one of the factors that drives evaporation. And so a big airflow is going to promote evaporation because it's going to be transporting in dry air. Dry air can absorb the incoming vapor more easily than moist air. Moist air would mean that it has a relatively small gradient between saturation, which is all the moisture that the air can hold. That's saturation. So if you have 95% humidity, that means the air is already pretty full of moisture. It can't hold very much more, and so the rate of transport is going to be relatively slow. So that driving force is what the aerodynamic method takes a look at. Now, this next figure that just came up is a look at how the velocity of air varies as a function of elevation. You remember the no-slip condition from fluid mechanics, and that said that we can't have two objects, not objects, but we can't have a fluid in contact with a solid or another fluid and have it anything other than at the interface between those two the same velocity. And so even though the wind is moving at some elevation potentially very fast, down at the surface where we've got the water, the wind velocity is very low. Now, you'll notice here that they've drawn some ripples in the water surface, and that's going to be another factor that comes into the empirical approach for the aerodynamic method. Why do you think whether the water surface is glassy smooth versus whether it has some ripples and waves, why do you suppose that could have an effect on the rate of evaporation? What do you mean? If what hits the ripple? Well, the water itself is the ripple. And so, you know, the ripples are just these little waves in the water. And so the air is moving over it, and that's maybe what's causing the ripples. What do you think the difference in surface area is when you've got ripples like that? Yeah, it's similar to, in some ways, you know, when we talk about porosity of a soil, and if there is a large surface area, then there can be a bigger charge. Well, here the surface area of the water is greater if you've got these peaks. And so just think about the length of the line. If this was just a flat line, then the overall length of that curve would be less than now when it's peaked like that. And so the more disturbed or agitated the water is, the more the evaporation is going to be, just because it increases the surface area. And it's not just because of the surface area, it's also because some of the liquid is going to be up into this zone where there's more velocity. And so you're putting the location where the evaporation is actually happening up into a zone where there's more transport. Now another, excuse me, another factor that's going to be included in the aerodynamic method is the difference in temperature between the air and the water. And the reason for that is that air temperature affects how much moisture can be held in the air. And so as air temperature increases, so does the amount of water that can be held in it. And you'll remember that from when we were talking about precipitation, where as the air cooled, it couldn't hold as much moisture, and that's why it precipitated. So the opposite of that is as air is warmer, it can hold more moisture, and the way that we keep track of that is the vapor pressure. And the vapor pressure is simply the relative fraction of the air that is comprised of the liquid. And so, you know, some of the air is going to be oxygen, some of it is nitrogen, and some of it's going to be water vapor. And the vapor pressure gives us an idea of both in the liquid phase, how the propensity of it to go into the vapor phase, and then also you can measure how much moisture is in the air through its vapor pressure. Here's a figure that is showing as you go up, the humidity is decreasing. And that's one of the effects we talked about already, is just that when you are very close to the water surface, that's the source of the evaporation, then of course the humidity is going to be high. Now specific humidity is just the humidity relative to how much can be held there. So you can think of it as like a percentage of saturation. All right, so here's the approach we're going to go through. We have to estimate the saturation vapor pressure, and the saturation vapor pressure is going to, saturation vapor pressure is going to be given, but then the ambient vapor pressure we multiply by the relative humidity. And the example that we're working, the humidity of 75%, that's pretty high. It would be unusually humid, but maybe not out of the realm of possibility. Basically, the procedure we'll go in is, based on the temperature of the air, estimate the saturation vapor pressure, then we find the ambient vapor pressure. This factor B is the vapor transfer coefficient that depends on the relative height of the waves and some elevation that we're measuring the wind at. So U2 here and Z2 are related. Usually you wouldn't be measuring the air speed right at the water surface. You know, whatever instrument you're using couldn't be immediately at the water surface, and so it's some distance above the water surface, Z2, that you're measuring the wind, and then U2 is going to be the actual velocity of the wind. I'll point out that just the way that this empirical equation is constructed, that the temperatures that you should use for the air are going to be Celsius rather than Kelvin, which is sometimes a little bit more normal for us to be using Kelvin. All right, so let's try out how that works. From the previous example, if you've got your notes there, when we were doing the energy method, we found that the evaporation rate would be 6.54 millimeters per day. That's just based on how much energy was available to drive evaporation. But you can only have that much evaporation if you've got enough transport to get the humidity out of the way. And so you may have, let's say, for instance, you've got a factory that's generating a lot of something. Well, you have to have trucks to take that product out of the factory in order to be able to deliver it to the customers. And so here, the factory that's driving evaporation is the energy, but then we also have to account for transport as well. And so this aerodynamic approach is going to say, you know, of the 6.54 millimeters per day, do we have enough transport to actually move it all out of the way, or is transport going to somehow limit the actual amount of evaporation? All right. So here we have the humidity is 75%, the wind speed is 1.7 at 2 meters. So the at 2 meters means an elevation of 2 meters above the water surface. That's going to be the Z2. The Z naught is the height of the water ripples. So 0.03 centimeters. And you'll notice that the Z1 and Z2 ratio is in a logarithm, and so they need to be in the same units. So you'll need to do a conversion to get the Z2 and the Z0 into the same units. All right. So I'm going to pause the recording for a moment, give you some time to start calculating these, working from the top downward until finally we have E sub A. And the units that will come out of that is going to be meters per day. And so you'll need to convert that. Now hold on a second. No, actually, if the B, the units that we get out of B will be millimeters per day per Pascal. Yeah. So let me, for B, if you use U2 is meters per second, and then the logarithm of this elevation, you'll have either centimeters or meters for both of them. It doesn't matter as long as you use the same units for each. Then B is going to have units of millimeters per day pascals. All right, so calculate E sub AS, 3893 pascals, and that's basically just based on the air temperature. And then E sub A is based on that and the relative humidity. And if you look later on down here at the bottom, we were talking about a gradient earlier. The difference between how humid it is and how humid it could be is one of the driving forces. And so here, this gradient, E sub AS minus E sub A, is taking that into account. And so the bigger that difference between the vapor pressure that could be in air if it was fully saturated with moisture and the actual vapor pressure of the air, so the larger that gradient, the larger the evaporation is going to be. And in this case, there's a relatively small gradient because the humidity is so high. 75% humidity means that the difference between E sub AS and E sub A is pretty minor. And then the factor B, when we're talking about the driving forces, is it accounting for the wind speed? And so the relative effect of the wind speed and the wave height. And so if we had more wind, then there would be more evaporation because U2 is in the numerator here, and then we're multiplying the gradient, that difference between E sub AS and EA, by the B that we calculate. So it turns out that if we account for just the aerodynamic component of things, we'd predict 2.18 millimeters per day compared to 6.54 if we were just looking at things from the energy side of things. Okay, so any questions about this example before we look at how to reconcile the two? No, we don't add them. It certainly wouldn't be any more than the energy that's available. If you wanted to say, we could potentially have what was it, 6.5, from energy, 6.54. We can't have any more than that. What we do to say, well, which is it, is this combined method. So if you had unlimited energy, then you would use the vapor transport to find out the limiting factor. But these two methods that we've just been using so far, the energy balance method assumed that you had unlimited transport, and the aerodynamic method assumes you have unlimited energy, and neither is actually true. And so this combined method is kind of a weighted average for accounting for the limitations of each. And so you'll notice that you have to take the amount of evaporation predicted by the energy balance and by the aerodynamic approach. That's not right. Aerodynamic and vapor transport's the same. I think I meant to say E sub R was the energy. So. All right. So the first term accounts for the available energy. The second term accounts for vapor transport, or the aerodynamic. And we have to calculate these weighting coefficients to find out the relative proportion of each that comes into the overall whole. And one of the terms, this gamma, is the psychometric constant. And it is related to, for the gas in question, how much of the air is moisture, and then the latent heat of vaporization. So it's a constant that we don't necessarily have to calculate if we're at sea level where the pressure is pretty close to 101 kilopascals, but if you are doing evaporation in like a high mountain lake and you actually had changes in air pressure, and if you had a water temperature that was pretty outside of the normal, but this value of 66.8 pascals per degree Celsius is for kind of like a typical water temperature and sea level conditions, where the molecular weight ratio of air to water has been calculated, and that would be a constant regardless of where you're at. The delta term, we actually do have to calculate that on each basis. It's not just a constant we can always use, because the air temperature is going to be varying, and we can use the E sub AS that we calculated before when we were doing the aerodynamic method. So this combined method is sometimes just thrown out the window in favor of something called the Priestley-Taylor approach, which says the evaporation rate is going to be about 1.3 times whatever is predicted by the E sub r term of the combined method. And so if you were doing that, then you wouldn't even have to calculate the aerodynamic. So let's try out both. Let's try the full-fledged combined method and also the Priestley-Taylor abbreviation just to see what we get. So you previously calculated in the steps before that E sub r was 6.54 millimeters per day, and the E sub a that we just did in the previous example is 2.18 millimeters per day. So now what we need to do is calculate delta and then use it to compute E with the full combined method, and then see what that says in terms of millimeters per day and compare it to the Priestley-Taylor approach. Okay, so we're basically doing a weighted average. It's going to be somewhere in the middle between assuming that you've got unlimited transport and unlimited energy. And so that middle ground here takes into account both the aerodynamic and the energy method, how much was predicted there. And what we're saying is it's going to be about 77% of the energy estimate and about 23% of the, in this case, the aerodynamic method, and so we would expect 5.55 millimeters per day of evaporation. And this is talking about evaporation from an open liquid. And so if it was wet soil, then that would be different. If it was evaporation from plants that are containing moisture, that would be different. This is evaporation from open water that's in direct sun. Now, the Priestley-Taylor estimate says that usually you can estimate the amount of evaporation by not even looking at conditions for the aerodynamic approach. You know, they're using typical values of wind speed, typical values of temperatures, and so on. And so the Priestley-Taylor method here is going to be predicting quite a bit more evaporation than the combined method did, because the Priestley-Taylor isn't accounting for the relative humidity. You know, it's just using the average atmospheric conditions. In this particular example, we had a relatively high 75% humidity, and that's what brought our combined method average down to 5.55 compared to this Priestley-Taylor estimate. So, you know, depending on the assumptions, the Priestley-Taylor and the combined method can be very close. Like I told you, I changed the numbers on this example to make it more interesting. Well, in the past, when I had, I think, 55% humidity and 2.7 meters per second, the Priestley-Taylor and the combined method were actually very, very close. It's just when I kind of brought the humidity up because I wanted the aerodynamic method to show a different value than the energy method. So hopefully what this gives you is just kind of an understanding of the fundamentals that drive evaporation. And if you were actually going to be doing anything more than just a very brief study of evaporation, then you wouldn't just rely on models like this. You'd actually do physical measurements. You'd use pans. And that's what we're going to talk about next, is these evaporation pans that can be used to not only measure the amount of evaporation of open water, but also extrapolate that to the behavior of crops and evapotranspiration. So here ET is an abbreviation for evaporation from crops, and that's called evapotranspiration, when it's both the evaporation and the surface of a plant sort of exhaling moisture. That's the transpiration. And so the way it works is that there is a certain amount of water that's put into a pan, and then over time you measure how much the water level goes down from the pan. And of course, if it rained during that period, you'd find the net difference between how much water came in and what the water level change was. You can do these evaporation measurements in open water. Like this is kind of an interesting contraption where they've got basically a swimming pool of sorts, like a small plastic kiddie pool out in a lake, and they're measuring the decreasing depth of the water inside of that secondary basin there to get an idea of how much evaporation there was for the lake. Now, the nice thing about this is that it directly takes into account the air temperature, the solar radiation, you know, all those driving factors that would be hard to put into a model, and you're probably not going to have data on an hour-by-hour basis that's predicting the solar radiation or the air temperature or the changing air pressure and the humidity. I mean, if you think about it, this is a physical integration of all of those factors continually over time. And so you'll potentially get much better results in predicting how much evapotranspiration there was using a pan. The thing that gets a little bit tricky then is relating the performance of a pan to crops, because different types of crops transpire water more easily than others. You know, there can be very waxy leafed plants, like pineapple, for instance, is a plant that really holds on to its moisture, and it has very low evapotranspiration compared to things like grass. You know, the grass that we plant in our yard, because the leaves are relatively thin, because there's a lot of them, evapotranspiration can be relatively high. And so this table, what it is a table that would relate a crop to how much evapotranspiration is observed from a pan. And the way that you'd use this table is, you'll notice the main data that we're looking for is some decimal that is less than 1. And we'll talk about the different trends that are accounted for in this table, but once you have that K sub p, the pan coefficient, which is a decimal less than 1, then you'd multiply it by the evaporation that was observed in the pan, and that would tell you how much evapotranspiration occurred in a crop of interest. And so there would be different tables like this for different crops. There may be a wheat table, there would be a different table for corn, I suppose a table for pineapples if we were keeping track of that. But let's first of all identify the effect that this table is ascribing to wind speed. So you'll notice here are different sets of rows for everything from light wind, moderate, strong, and very strong. And so all other things being equal, for instance, the humidity being equal and the upwind fetch being equal, so the first row in each of these groups, we're going from 0.55 to 0.5 to 0.45. So the more the wind is, what we're saying is that your evapotranspiration is going to be less than that which would be predicted by the pan. So in other words, plants aren't going to be as affected by wind conditions as open water will, because the evapotranspiration process is where moisture is being emitted from the pores of plants rather than just from some open water source. So the windier it is, there may be more evaporation, but the relative fraction of evaporation in the plant to the evaporation in the pan is decreasing. So that's the first trend, the wind speed trend. The next is upwind fetch. Now, I need to even tell you what the upwind fetch is. That is, you can put the pan in a lot of different locations. And so let's say that we had a field, and we're growing corn in that field. So here's our crop. Each one of these lines represents a stalk of corn. We're really putting the effort in today for the drawing. So let's say here's our pan, and we're modeling evaporation there, and the breeze is coming this way. So if you have the pan in the middle of the crop, then this is the upwind fetch. It's just saying, where is the pan relative to the rest of the crops? And so the effect here of upwind fetch is that as the upwind fetch increases, it gets closer and closer between the pan coefficient, what you're observing in the pan, and the actual evaporation of the crop. And the reason for that is that the upwind fetch, in effect, it is the air is more humid as the air has contact with some upwind fetch before it gets to the pan. So if we had the pan instead before the crops, then the air is going to be less humid when it gets there on a relative basis, because we haven't already had a lot of transpiration occurring. And so you have to keep track of not only how windy it is, but also where the pan is relative to the rest of the crops. And then the other factor you'll notice here at each of these columns is the humidity. And so as the humidity goes up, then the pan coefficient gets closer to actually represent, for the evaporation observed in the pan to be actually the evapotranspiration. So if the pan coefficient was 1, then that would mean that whatever you observed in the pan is exactly how much evapotranspiration occurred in the crop itself. But the further away from 1, when you have it lower, that means that the pan is showing more evaporation that actually occurred inside of the crop of interest. And so low humidity lends itself to the pan exaggerating the amount of evaporation, whereas a high humidity means that the pan and the plants are going to be closer together in how much evaporation there was. All right, so these are relatively simple calculations, but let's just try it all the same. Let's say that we've got an average wind speed in northeast Ohio of 2.7 meters per second. Mean relative humidity is 65%. And so if we have an evaporation pan that's measuring 4.2 millimeters of evaporation per day, and the pan is located, it's surrounded on all sides by 100 meters of dry fallow. I guess that's one other factor I didn't mention, is that we have 2 sets of tables here. This is if the crop is actually growing, and the secondary case is by dry, bare area. And so fallow means that the field is basically empty. It's not actually growing an active crop at that time. So here in this illustration, the pan is surrounded by 100 meters of dry fallow on all sides, and it's measuring 4.2 millimeters of evaporation per day. So that's the E sub P. So the 2 questions we're asking is, what's the monthly reference evaporation for short irrigated grass turf, which is what this table is for, short irrigated grass turf. And then second, how much irrigation should farmers provide? All right. So I'm going to leave it, once you copy down this info, I'm going to move it to back to the previous table so you can find the pan coefficient that you need. So we have to find out which K sub P to use the E sub P is easy enough. That's just the pan itself measured 4.2 millimeters of evaporation per day. So finding the correct K sub P is what we need to look up on this table. Okay, so since it's case B, since it's bare fallow in the example, that means we're case B, surrounded by dry bare earth. And the wind speed of 2.7 means this moderate is where we're looking. And it's 100 meters of upwind fallow, so it's going to be this row. And then the humidity of 65% puts us in the medium range. And so that's the value, 0.60. Because case B, since it's surrounded by a non-growing crop, moderate wind puts us somewhere in here, 100 meters of upwind fetch, and then medium humidity. So 0.6 is the K sub P, 0.60. So now it's asking what's the monthly evapotranspiration? All right, so the pan is evaporating 4.2 millimeters per day. We know that the grass is going to evaporate less than that. What we're saying is, based on the conditions and the coefficient table that we have, we think that the grass is going to evapotranspirate 60% of what's happening in the pan. So on a daily basis, that means evaporation of 2.52 millimeters per day. And so assuming 30 days per month, then that means we would expect evapotranspiration of 75.6 millimeters per month. So that's how much the grass is, how much moisture the grass is exhaling through evapotranspiration. And so this is asking then, well, how much irrigation should a farmer provide? And to answer that question, we'd have to know how much precipitation there is. And so it would be the difference between the amount of irrigation to provide would be whatever evapotranspiration is occurring minus the precipitation. And this is the first time that we've kind of thought about a water balance. And we're going to do this a lot more, especially when we start talking about runoff, the idea of water balance. And so if you think about the water has to go somewhere. It's either going to infiltrate down into the soil, or it's going to be incorporated into the mass of the plant, or it's going to evapotranspirate into the atmosphere. So this is the simplest conception of a model. This is saying, assuming that all we want to do is overcome the evapotranspiration. If we're neglecting the additional water needed for plant growth, if we're neglecting any water that gets down into the soil, if we're saying all we're doing is making up for evapotranspiration, then the irrigation would have to be at least as much as the evapotranspiration, but we know that it might rain. So if it rained, you don't have to provide as much irrigation. So that's what this model is kind of assuming, is there are a lot more factors that actually accounts for where the water is going. And we will talk about those factors later on, but irrigation to provide is at least, at the very least, the evapotranspiration minus precipitation. And so there are plenty of places, especially out west where a lot of crops grow, and there's no precipitation at all during the growing season. This past summer I was out in Idaho, and just the area I was at, they have a lot of cattle farming there, and so people grow alfalfa and grass crops, and they have to irrigate all of it because there's no rain during the spring months. At least while I was there was no rain, and so they pump water up from the river. That's mountain runoff from snow melt. They pump it from the river, and then they just irrigate all night long. Farmers get up in the middle of the night, move the lines, irrigate for 8 hours, move the lines again, and they're constantly just trying to overcome evaporation. So what about corn? What would you expect compared to grass? Well, here's a figure that addresses that. Different types, the relative demands of different grasses. And so what this figure is saying that, let's see, grass as a reference is this line here. And here is a grass as a reference. And so maize is another name for corn. This is actually saying that you'd have more evaporation for corn than you would for grass. And the reason for that might be because if you think about how tall a stalk of corn is, there's a lot more surface area to the plant mass that's there. And here's at mid-season another view of corn. And this is like the range of values, whereas this is just kind of like point values. So there's been a lot of research in agricultural journals. They have done field studies of evapotranspiration of different crops and relating it to pan coefficients. So using grass as a reference, trying to predict how much water is going to be needing for each of these other crops. Any questions about evapotranspiration? All right, so what we're working towards is an idea of a water balance where we have to account for the entire water cycle. Increase in soil moisture when it rains, the transport down to the saturated zone, the movement of groundwater through the saturated zone, the relative fraction of runoff that's leading to flow in streams and so on. And evapotranspiration is usually considered a pretty minor factor in the overall water balance. It's a major factor for those who are growing the crops, but that's all we have for today as far as evaporation. Let's take a look at these announcements here. All right, so the homework is due on Thursday, the midterm exam a week after that, and I've got office hours this afternoon, tomorrow, and Thursday. If you have any questions on the homework or if you want to check your answers or anything like that, just let me know. Oh, you're right. It is homework 5. 4 was precipitation, right? Yeah, thanks. So it's the homework that I handed out. It's available on MU Online, but yeah, homework 5. All right. Have a good one.